Hello Legacy Sabers, Marsh here. This is video 3 of 4 for the final semester 1 packet. We will continue in our look at unit 4, which was on special functions. We are now going to work on how to solve an absolute value equation. So on number 15, first thing I notice, there's stuff around the absolute value, right? So we needed to make the absolute value be alone. So I'm first going to add the 2 over. So I'm going to get 1/2. I'm going to go over here. 2x plus 3. And that's equal to 9 now, right? Now, I got to get rid of that 1/2. Can't distribute into absolute value. No. Don't do that. But I could divide by 1/2, but that's just gross. I'm going to multiply by the reciprocal. So I'm going to multiply by 2. Oop, there we go. And then I'm going to get 2x plus 3, still an absolute value, is equal to 18. Now, absolute value is completely alone. Now remember, how did we solve this problem? Well, we had to drop the absolute value bars. But to drop them, you had to look at 2 problems. Because remember, an absolute value function has 2 arms, right? So there's 2 problems, a positive slope and a negative slope. So I'm going to do a positive version of the problem, and I'm going to do a negative version of the problem. And I'm going to solve them both. Well, this one, I'll get 2x equals 15, right? Subtract 3. And then I'm going to get 15 over 2. Now remember, here's the problem with these problems. Sometimes they pull a gotcha moment, and we have to check the original. We have to check the answer in the original, make sure it actually works. Well, 2 times 15 over 2, that's just 15, right? Plus 3, that's 18. Absolute value, still 18. Times 1/2, 9. Minus 2, definitely 7. Big giant check mark. It definitely works. Let's try this next problem. So I'm going to distribute the negative. Ooh, add 3. Marsh didn't give herself a lot of room over here. Bad Marsh. 21. X is negative 21 halves, it looks like. Again, let's substitute. 2 times negative 21 halves is negative 21. Add 3, that's negative 18. Absolute value, though, is a positive 18. Times 1/2, 9. Minus 2, definitely, in fact, 7. Both of them worked. Now remember, you could get it that neither of them work. You can get only one of them work. Or in this case, we got both of them to work. It was a good day. Next problem here was a piecewise function. Remember, basically, we graphed the function like normal, and then we took care of where it exists in the problem. So I'm going to put a little dot here. First thing, got to graph this v. So I'm going to make myself a little parent table down here. So same parent table as we used in our last video, because it is a v. Reflection, so everybody's going to get a negative tacked on. I've got to subtract 5 from my x's, and I'm going to add 4 to my y's. So my parent table here is -7, -6, -5, -4, and -3. And 2, 3, 4, 3, and 2. It looks like would be my y values. So I'm going to graph this v with the dots. I'm not going to actually draw the lines, but I'm going to graph the dots. 1, 2, 3, 4, 5, 6, 7, up 2. -6, up 3. -5, up 4. And then down. Now, notice, I can only have this graph as long as my x values are smaller than -3, which would be right here, right? That's where -3 is. So on the left, I'm allowed to have this graph. So I'm going to make sure that the left side of this graph, left side of -3, I have the graph. Then I'm going to look. It is a equal to, so that means I need a big, nice, big, giant closed dot there. I'm now going to graph another function. So I'm going to change my color so that way you guys can see x minus 4. So I'm just going to graph that like normal. I'm going to go down to -4. I'm going to put dots everywhere here so you guys can see it. Reason why I'm putting all these dots is I don't know where I'm going to keep this graph. I need to keep this graph so it's between -3 and 1. So I'm going to erase all the dots that are between or not between -3 and 1 on the x's. So between, okay, these guys are not. And then 1. So I can't have anybody past that. So I'm going to erase all these dots. I'm going to draw in my dots now. I'm going to actually connect the dots. Whoop. At least I thought I was. Now, -3. I don't have an equal to. So that means at -3 on the x, I need a big giant open circle there, an open dot, showing that I am not including it. But at 1, we do have inclusion. We have an equal sign. So I'm going to put a nice closed dot there. Got one more function to graph. I'm going to go to, what other color do we want to put on here? Let's put some green. That looks fun. Let's graph 3x plus 2. So I'm going to start at 2. Go up 3. 1, 2, 3, over 1. And I'm going to do that a bunch of times. I'm going to do that all the graph, even though I know I probably don't need it all, but that's okay. Ooh, connects the dots right there. That's kind of neat. Okay, I can only have this function as long as x is 1, bigger than 1 in this fact. So I'm going to go to my eraser. Bigger than 1 is on this side, so I can't have this, nor that one, nor that one, not this little, oh, I just erased my graph. Silly Marsh. Fix that here. Oh, I think I picked the wrong. Yeah, all right. Blue is blue, right? There we go. I'm going to go back to my green. So I'm allowed to have it as long as x is bigger than 1. So I'm going to connect my dots on this side, put an arrow showing that I can go forever. And then I am not able to include 1, so I do need to put a big, nice open dot at that graph. Look how beautiful that piecewise graph looks like. Let's continue. So now we're on solving quadratics, the 5th unit. First of all, we talked about factoring and solving. So you want to factor the problem and then solve. Remember, there's 4 different kinds of factoring that we looked at. We looked at GCF. Does everybody share something? We looked at grouping. That was when we had 4 terms. We looked at trinomial patterns, so basically 3 terms. And then we also looked at difference of squares. Difference of squares is when we had 2 perfect squares and subtraction in the middle. So this one I'm looking at, notice it has 3 terms and it's also equal to 0. Can't factor if you're not equal to 0. So I'm going to do trinomial patterns. So I'm basically going to do some guess and check. I'm going to ask myself, what 2 things make x squared? Well, in this case, an x and an x, right? How do you make 10? Negative 10 in this case, but I'm just going to think about 10. Well, 10 and 1. But ultimately, when I multiply my outsides and my insides, I need a positive 3. 10 and 1 aren't going to make, right? 10 and 1, that can't ever make 3. But 5 and 2, that can make 3. So I'm going to put a 5 and a 2 here. And how do I make a positive 3? Well, I would need a positive 5 and a negative 2, right? So no, positive 5, negative 2. But I'm equal to 0. So that means I have to set both of these 2 equal to 0. And I'm going to solve. Well, I would get x is negative 5. And I would get x is 2, right? Number 18. Hold on. They both have a 4. Let's get rid of that perfect square, or that GCF. R squared minus 1. Well, there's only 2 terms. Well, they're both perfect squares, and there's subtraction in the middle. Difference of perfect squares, it looks like. So that would be r plus 1, r minus 1. Because remember, you need that middle term to be a 0. That is why we know that this pattern works. I'm going to set both of these equal to 0. The 4 doesn't really matter, actually, because I could just divide the 4 away. So I'm going to get r equals negative 1 and r equals 1. Next one, I'm not equal to 0 anymore. Let's make it equal to 0. So I'm going to add 5x and I'm going to subtract 6 to the other side. Oh, sad day. No GCF. Let's do some trinomial pattern since there's only 3 terms. How do you make 4? Well, 2 and 2. Let's try 4 and a 1. So 4x and an x. How do we make 6? Well, 3 and 2 and 6 and 1, right? I'm going to try a 6 and a 1. So I'm going to put a 6 here and a 1 there. So I'm going to multiply my outsides. So 4x times 1 is 4x. 6 times x is 6x. Oh, dang. That's never going to make 5. Well, I can't do that. And I definitely don't want to flip that 6 and the 1 around because then I'm going to get 24 when I multiply the 6 and the 4. That's not going to work. Let's try 3 and 2. So I'm going to go, well, you know what? I'm going to put a 3 here. No, because that's 12. That's really big. Let's try a 2 over there. 3 here. So 4x times 2 is 8x. 3 times x is 3x. That can make me a positive 5 if I had a positive 8 and a negative 3. So I'm going to go negative 3, positive 2. So now my two answers to this problem, I'm going to get x equals 3/4 from this problem and x equals negative 2 from that factor. The next thing we did is we solved by square roots. So I need to get the x squared alone, just like you would get x alone on your normal problems. So I'm going to add 7 to both sides. And I get 495 out of that when I add. I'm going to divide by 5. That gives me an answer of 99. Now, I need to solve x squared. So I'm going to square root both sides. Well, square root of 99 probably breaks down, right? I need to find a perfect square that goes into 99, which in this case is 9. I also know that 9 times something makes me 99. Well, that would be 11, right? Square root of 9, that's just a 3. So if I write my answer, don't forget though, if you square root, you get a plus or minus when solving. So I'm going to get 3 square roots of 11 for my answer to number 20. 21. Ooh, lots more stuff. I'm going to worry about this guy later. I want him to be alone. Basically, I want the x squared alone. So I'm going to subtract 2. I'm going to divide by a negative 3. Now, x squared guy is alone. I'm going to square root both sides. So I'm going to get x minus 3 equals, well, square root of negative 8. Well, remember, when you got a negative under the radical, that meant we got an I in there, right? Because the square root of negative 1 was I. That took care of my negative. So then I'm just looking at the square root of 8. Well, square root of 8 has a square root of 4 and a square root of 2, because 4 times 2 is 8. Square root of 4 is, in fact, 2. So this can simplify down with a plus or minus in front, of course, as 2i times the square root of 2. I now need x alone, right? Because he's not alone yet. I'm going to add the 3 over and just set it in front, just like that. And the last problems that we did was on complex numbers. Remember, in standard form meant that the real portion came first, so just the normal number without the I. First thing is we just did some simple operations with them. Well, subtraction. I'm going to distribute that negative into the other problem, so then I can actually see what's happening. There we go. Now I'm just going to combine some like terms. 5 minus 2, that's 3. 2i minus 3i, negative I. That is my answer to that problem because I cannot combine a real and an imaginary. Let's FOIL for this multiplication. So I'm going to do 2 times 4, that's 8. 2 times I, that's 2i. Negative I times 4 is negative 4i. And negative I times a positive I is negative I squared. Hold on. I squared, that was just equal to negative 1, right? Do you remember that when we talked about that? Well, so isn't this just back here a negative 1? Plus I can combine some like terms. So this is technically subtracting a negative 1, which is plus 1. So I got 8 minus 2i, that's me combining my i's, plus 1, or 9 minus 2i if I simplify just a little further. The other term, the other thing that we did is we had to simplify powers of I. So we also knew I cubed, which was a negative I because that was I squared times I, right? So negative 1 times I. And then we also had I to the 4th, which was an I squared times an I squared, which is a positive 1. Some notes that I would make sure you have, all right? So now I had to think to myself, how many times can I go through my pattern that I have as I to the first is I, because there's only 4 different answers I can possibly get to an I to the 54th. So either we saw how many times can 4 go into 54. So I'm going to see how many times does 4 go into 54? How many times can this pattern hold? Well, 4 goes into 5 one time, right? 4 goes into 14 3 times. I'm left with a remainder of 2. This remainder meant I have 2 I's left behind after I go through my pattern 13 times. So I went through this 4-person pattern 13 times. I have 2 I's left to go. That means I have an I squared left, right? Which would mean this I to the 54th is technically just a -1. Which means -4 times I to the 54th is just a +4. The other problem that we did here was division. And remember, we couldn't have an I in the denominator. It was kind of frowned upon. So we had to multiply by what's known as the complex conjugate. So we had to multiply the top and the bottom by the denominator, but a little sign change in the middle. So we're going to do a plus. And then we just multiplied. I'm going to back over here so we can actually see what we're doing. So 2I times 3 is 6I. 2I times 9I is 18I squared. Now I got this denominator. Gross, tons of foiling. 3 times 3, 9. 3 times 9I, 27I. -9I times 3, -27I. -9I times 9I is -81I squared. Ooh, well, 27 and -27, those guys are going to cancel out, right? I squared, we knew that to be -1. So technically that numerator, is -18, right? Because this is -1 times 18, -18, plus 6I. Same thing here. This is technically a -1, so that's a +81, plus a 9, which is 90. And just wait a minute. I bet all these have a number in common. They definitely all have a 2. No, they definitely all have 3, though. Do they have a 6? 90 divided by 6? Oh, you're right. All of them have a 6 in there. So we're going to divide all of these terms by 6. I'm going to get -3 plus an I all over 90 divided by 6 is 18. Who would have thunk? That is the simplified version, simplified, of number 25. And that is the end of video 3 of 4. You're almost done with the review packet. Continue on to video number 4, the final video, and I will see you guys there. See you later, savers.